In this video, we will discuss some bit manipulation techniques that do not have an explicit name but are very useful in solving bit manipulation related problems. Let's start with a very simple problem. You have an array containing n elements. Suppose this is A1, this is A2, this is A3, and this is A4. And your goal is to compute the bitwise and store it in this green box. You have to compute the bitwise AND of all the elements A1 and A2 and A3 and A4. So this problem is very trivial to solve if you use the inbuilt bitwise AND operator. But do you know how to solve this problem bit by bit? And do you know why it can be solved bit by bit? This is because by definition, it says that you have to compute the bitwise AND. That is, you have to arrange all the numbers in a line, write down all their bits, and then take their bitwise AND. So each cell in a green box that you see, they represent one bit of the number. So here we are assuming that one number can have maximum of 6 bits. But in general, this number will be 30. Why? Because 2 to the power 30 is very comfortably greater than 10 to the power 9. Therefore, any number can be represented in at most 30 bits if that number is less than or equal to 10 to the power 9. So suppose that this is the bit position 0, this is the bit position 1, this is bit position 2, 3, 4, and 5. Now if I ask you to solve this same problem but bit by bit, then you can simply iterate over each of the elements, or first iterate over each of the bits and then iterate over each of the elements at that bit position and then compute their bitwise AND. For example, if all the elements have a 1 set at bit position 2, only then the bitwise AND would contain 1 in the result. But if at least one element has a 0 set over here, then no matter what other elements contain at this bit position 4, the final result will always be 0. So that is how you can compute the bit position, and the time complexity would be log of max, where max is the maximum value in that array. So this number is usually 30. So the time complexity would be 30 into n if you are just dealing with integers less than or equal to 9. So this is how you can solve the problem bit by bit instead of using this inbuilt operation. So far so good, right? This problem is very easy to solve and everyone knows that you can solve it bit by bit, and it's very simple. So let's make this a bit more complicated. Let's go to the next problem. And in this problem, suppose you are given an array and you have to compute you have to compute this expression, summation of AI bitwise and with AJ. Okay, you have to compute the sum of bitwise and of all AI and AJ, where AI and AJ are a subsequence of length 2. A subsequence of length 2. So given this array, how do you efficiently compute the bitwise AND of all the subsequence of length 2 and then sum them up, right? So for example, this is one subsequence of length 2. So you compute their bitwise AND, you add to the final sum. Then this is another subsequence of length 2, you compute their bitwise AND, and then you add it to the result. So how do you solve this problem efficiently? So of course, you know that there can be a lot of subsequences, so computing them naively is not feasible. Okay, so let's discuss the first important idea of this problem is that even though the problem is talking about subsequence, in most of these problems, these subsequences, they can actually be simplified down to subsets. Now, what is the difference between subsequence and subsets? Subsets are unordered. So this makes it very easy to think about what's happening with them. But subsequences are ordered. So you will see that even though the problem asks you to do something with subsequence, but what do you do with that subsequence? That is commutative, right? In the sense that AI and AJ, bitwise AND of AI and AJ is equal to bitwise AND of AJ and AI. So even though the problem is asking you to deal with subsequences, but if it is not really getting the benefit of the ordering of the elements, it makes much more sense to think about all subsets of length 2. So if you can compute the answer, if you can compute the answer for all the subsets of length 2 of size 2, then you can notice that the answer remains the same. So this is one major takeaway that you can have from this video, is that when the problem asks you to deal with subsequences, but it doesn't really utilize the benefits of the subsequence, that is, if it doesn't rely on the ordering of the elements to compute something, then you are free to alter that subsequence to a subset, right? So for example, you might have heard of this problem called maximum sum subset. Okay, so if I give you an array and if I tell you to tell me the maximum sum of all the elements possible in all the subsets that are possible, so I can also rephrase that same problem via the subsequence method. I can ask you the maximum sum of all the elements of any subsequence. So you can see that both this problem, this subset one and this subsequence one, they are equivalent, because the sum of elements in a subset is equal to sum of elements in a subsequence. Their ordering does not matter. So this has simplified the problem a bit, but hasn't really shown us how to compute the bitwise AND, right? That part we are yet to go over, right? So now let's see why computing the bitwise AND bit by bit does not work, right? Because that is the first idea that you might think of. So let's see what's the problem with that. So assume that you have this array, and as usual, this is A1, A2, A3, and A4. Now, when you're computing the answer for this particular bit position, and suppose it has 1, 1, 1, and 1. Now, what do you think? Like in the final result, should there be a 0 over here or should there be a 1 over here? Because if you said that there should be a 1 over here, then you are wrong. Because even though the bitwise AND of all of these elements is equal to 1, doesn't mean that there has to be a 1 in the result over here. Why? Because of the concept of carry. So you know that since we are dealing with the summation, right? Binary addition, we are dealing with this, right? AI and AG, right? We are dealing with this. So it might happen that there is some carry forward, like let's say this overflowed, right? And then it carried forward from here. So this one will actually transition to 0. So this is the major hurdle in all of the bitwise related problems. As soon as they uh, start getting together with this summation. So that's why summation and bitwise operator, they do not go well, right? Because of carry. So the second major takeaway is that if I can show you a way to avoid carries altogether, but still treat all of these bits as independent, like that would be a major advancement, right? That will help you to now focus your entire attention on a single bit instead of worrying about any of the carry that might come in for a particular bit position. But how do you exactly get rid of a carry, right? Like uh, whatever algorithm we might try to come up with, you might think that it is impossible to get rid of a carry and then still think about each bit position as independently. But once you say it, it's difficult to unsay it. So let's directly look at the algorithm that eliminates all the requirements of a carry and then still treats all the bit positions as independent. Okay, so if you have all of these array elements and you have to compute the bitwise AND of all the subsets of size 2, then you can see that if I have this binary representation 1 0 1 1 0, then each number has a unique uh, binary representation, but you can also sum it, you can also express it as a sum of 2 to the power I. So if you label this bit position as 0 1 2 3 4, so you can write this number as 2 to the power 4 into 1 plus 2 to the power 3 into 0 plus 2 to the power 2 into 1 plus 2 to the power 1 into 1 plus 2 to the power 0 into 0. So this is the binary representation of this number in terms of powers of 2. So if you start thinking of any number in as this, right, summation of powers of 2, then you will not have to worry about carries immediately, because assume that all of this bit position is 1, right? Then you focus on something known as the contribution technique of each of the bit, right? So you worry about how much each of the bits will contribute instead of worrying about if there is any carry coming over into this bit or not. So if all of these elements are 1, right, if all of these elements are 1, then every time you create a subset of size 2, how many ways, first of all, how many ways are there to create a subset of size 2? So there are 4C2 ways, because 4 bits are 1 and you can select any 2 of these bits. So for example, what are these 4C2 ways? A1 A2, A1 A3, A1 A4, A4, and then A2 A4, A2 A3 as well, and then A3 A4. So there are 4C2 ways to select a bit, and then in all of these combinations you can see that uh, whatever AI and AJ, right, whatever the bitwise AND of AI and AJ is, instead of computing this in a bitwise, in a bit by bit fashion, you can instead express it as summation of 2 to the power I into whatever the coefficient is, whether it is 0 or whether it is 1 in front of that. So this means that these, like, there can be 4C2 choices in which this bit will be set. So these many times it will contribute how much to the final sum? It will contribute 2 to the power whatever the index is, 0 1 2 3. So 2 to the power 3. So you can see that each bit is now contributing independently, even though this can lead to carry, right? But then since we are counting the contribution independently and then we are storing the contribution here only, then it means that this carry is not propagating over here. So in this manner, you will only have to worry about the carry once you have contributed the, once you have calculated the contribution of all the bit position, and then finally when you are doing the sum of all of these bit position, then you can simply do something like this, like 4C2 into 2 to the power 3, then there will be some coefficient into 2 to the power 2, etc. So for some of you this might sound pretty obvious, like bit positions can be treated independently when you are dealing with 2 to the power I technique, and for some of you it might be completely new. So but this technique is very useful if you want to solve any problem that deals with summation as well as uh, bitwise AND or bitwise or bitwise XOR. Okay, so now let's see how we can solve the problem of computing all the computing the sum of bitwise AND of all subsequences of length 2, right, of length 2. Or let's say, what if you want to compute in general, right, like compute the bitwise AND of, like, if I ask you to do this, AI and AJ, AK and so on, like you compute the bitwise AND over all subsequences, which is basically equivalent to all subsets of size k, then you can see that now you can still treat each of the bits independently. Then you wonder how much this bit position, like bit position 0, how much will it contribute. So all that it matters is whether the subsequence that you create, whether that has the bitwise AND as 1 or 0. So suppose the distribution is 1 0 0 1, then you can see that for k is equal to 2, there is only one subset that will create a non-zero bitwise AND, right? There is only one subset. But if it had something like 1 1 0 1, or if it had like something like 1 1 1 1, then we saw that if we had this particular case, then it would have been 4C2. But if we had this particular case, then in 3 combination, so we have 1 in 3 places, right? So if you pick out 2 elements from this 3C2 ways, only then like you can create the bitwise AND as 1, like if you select this and this, or this and this, or this and this, right? So in general, you can notice that the contribution of a particular bit position matters only by the count of the bits that you have in those positions, right? So you can say that if there are a total of like let's say 1 ones in that position and zeros in that position, then you can notice that every time you include at least 1 0 in your answer, then the bitwise AND of the contribution of that entire bit position becomes 0. Why? Because you will add 0 into 2 to the power whatever that bit position is. So you have to select your subset from the number of ones that you have. So if I tell you that the number of ones in this bit position is like let's say m, then how many choices are there to select k ones out of these m ones, right? So that will be m times ck, right? And the 2 to the power b, where b is the bit position. So this is the like suppose this is the bit position. So this is the answer. So this is how you can compute for any subsequence. All you have to do is compute the total count of set bits at each bit position, and then the contribution of each bit position will be mck into 2 to the power b, where mck denotes the number of ways to create a subset of size k where all the elements are exactly equal to 1 at that bit position, right? So now you can solve this problem for any given k. And even if I give you something like, if I ask you that you are given an array a1, a2, a3 and an, and then you have to compute the answer for all the k, where k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4, and so on. That is, compute the bitwise AND of all the positions, compute the bitwise AND of all the subsequences or all the subsets of size 1, then compute the bitwise ANDs and then sum it up for all the subsequences of size 2. Then you should be able to do it, because we have concluded that the only thing that matters is the count of the set bits in each bit position. So you can actually get rid of this entire matrix thing, and you can just maintain a count array where you count how many ones are present in that bit position. So suppose that count comes out to be like 5 7 13 and 0 5 4, etc. Then when you are creating a subset of size 3, then how many times will this bit position contribute? So you can see that there are a total of 5 set bits in this lowest bit position. Then 5C3 times, like there is 5C3 ways to select a subset of size 3 where all the bits are set to 1, and this position will contribute 2 to the power 0. Then how many subsets will have how much contribution will this bit position give? So there are 7 set bits in this position. So it will give 7c3 into 2 to the power 1, and we don't actually care or worry about the carryover from this index. Why? Because we actually add their contribution directly. So we are creating the final number as the sum of powers of 2, and this trick that uh, like adding a number, like visualizing a number as sum of powers of 2 into some coefficients, this trick is what leading us to evaluate all the bit positions separately, right? So you can see that just by computing the count array, you can get the answer for all of this k. So we have learned 3 important techniques so far, right? One is one is that in each problem that deals with bitwise manipulation, you can instead do the operations bit by bit, and the time complexity would be log of max, whatever the maximum value is, which in general is 30. So 30 into n, this will be the time complexity. And then the second thing that we learned is that if the problem asks you to do something with subsequence but does not fully utilize the concept of subsequence, you can treat it as subset. Then the third technique we learned is that in some situations where it might look almost impossible to solve bit by bit, we can still solve it bit by bit via something known as the contribution technique, where you don't worry about the carry forwards from the previous set bits. Instead, you focus on what you can contribute by appending or multiplying the contribution, the coefficient by 2 to the power I, where I is the bit position that you are dealing with. And then finally, we saw an example of a problem where we can apply this technique, where the problem was asking you to compute the sum of bitwise and over all the subsequence or subsets of size k, right? And using this technique, we saw how you can do that, right? Now, if you've watched till this part of this video, you've already learned a great deal of things. But if you want to learn more, you can keep watching the video, or you can skip it because this part is going to be a bit more convoluted. But nonetheless, it like is still a standard technique. So let's start with this problem. And in the previous problem, I told you to compute. I told you to compute the answer for k is equal to 1, k is equal to 2, k is equal to 3, and so on, right? And you concluded that the answer only depends on the count of set bits for each bit position. Now, what if I reverse the problem? That is, I give you the answer for all of these k's, right? I give you n entries where each entry is guaranteed to be an answer for each k. And I ask you to construct an array with n elements that satisfies all of these k. Can you do that? So how do you even approach this problem? So to formalize the problem, basically for each k you are given the sum of bitwise and sum of bitwise and of all the subsequence of size k. So you have a subsequence or a subset of size k. You compute the bitwise and then you sum them up over all the size k subsequences, and that will be the answer f of k, you can say, right? And you are given f of k for all k from 1 to n. And your goal is to reverse engineer the array from this given f, and then compute the array, like if it is unique, print it. If not, just print any array that satisfies the condition. So now how do you approach this problem? So to approach this problem, let's see some more techniques. So let's start with the largest k, right? And we'll see why are we starting with the largest k, because largest k means bitwise and over all subsequences of length n, but there is only one subsequence of length n. So the last entry will be simply a of 1 into a of 2 into a of 3 into a of 4 and so on, right, up to a of n, and that entry will be present over here. So suppose this is f of n, right? And suppose this is nothing but 1 0 1 1 0 1. Now what can you conclude from f of n, right? because this, why are we starting with the f of n first of all? Because this does not involve any summation terms. So this might be easier for us to visualize. So what does this 1 mean over here? It means that you took the bitwise AND of all the elements, but you still ended up with 1. Means you can conclude that all the bits for all the elements must necessarily be 1 over here, right? So this part you can guarantee. Same for this, right? If it is 1, then all the bits will be 1 over here, right? But if it is 0, you don't know which bit or bits, like which array elements are having a 0 over there, right? But at least for the ones, you can be confident that these are the set bits for all of these elements. So, but why is this working for us? Because you can see that this number, right, it can be simply expressed as 2 to the power 0 into 1 plus 2 to the power 1 into 0, that is gone. Then you have 1 into 2 to the power 2 plus 1 into 2 to the power 3 plus 1 into 2 to the power 5, right? So this coefficient 1 that is here, this is helping us. Why is this helping us? Because we know that if it is 1, then it is not 1 because of carry, right? So carry is not involved over here. Why is carry not involved over here? Because whenever you add something with 2 to the power I, but you add the coefficient as 1, then there can be no carry involved, and you know that this 1 is formulated simply from these ones that you have, right? So far so good. Like with the last f of n, we can compute which elements have a set bit at which position, right? Like we can compute all the bit position where all the set bits, all the array elements have a set bits. But now let's look at the last second entry. Okay, let's look at, so you have a1, a2, a3, a4 and a5. Okay, now you want to find the answer where you want to find f of, let's say, n minus 1, that is compute these bitwise and of all the subsequence of size n minus 1 and then sum them up. So, and then suppose you get a bit representation like 1 1 0 0 1 1. Now let's see if we can infer something from this or not. Okay, now you are computing the bitwise and of all the subsequences or all the subset with size n minus 1. Now let's try to compute the answer bit by bit. Now when you're computing the answer for this particular bit index, then if this particular bit index has less than n minus 1 bits, right? If the total number of set bits in this particular bit index is less than n minus 1, then no matter which subset you select, there will be at least 1 0 that will sneak into that subset. And if so, then this result will always be 0, right? But if it is 0, then can you actually conclude that that the total number of ones is less than n minus 1? Can you conclude that? You cannot conclude that, because this 0, right, this could have been the result of a carry forward from the previous things, right? Because we are summing them up, right? So that is why it's not possible to conclude. Although in the previous version, when we are dealing with this one, it was very easy to conclude because there was no carry forward included. Okay, so okay, we know that if the count is less than n minus 1, it will be 0, but it is not possible to decide conclusively by just looking at this 0 over here, right? Now if this count is, so what can this count be, right? It can either be equal to n or equal to n minus 1, right? So if it is equal to n minus 1, then its contribution will be exactly 1, right? Because then there is only one subset in which all the elements are selected with the value 1, or if it is greater than 1, then its count will be n c n minus 1, because if it is greater than n minus 1, then it is exactly equal to n. So you see that right now it's not able to make any progress. Why? Because of these carry forward things. So what if we can formulate this problem where you are computing f of n minus 1 in terms of this, where you don't have to deal with carry forwards? So you can notice one thing, that if you have already concluded that all, in the previous iteration when you are finding out f of n, if you already concluded that all the set bits in the result, they represent that all the elements have a set bit in this bit position, then whenever you compute the subsequence of length n minus 1, then of course all of these they will also get involved. So how much carry forward will they uh, produce? So you can see that there are n set bits, and when you are computing the number of subsets with n minus 1 element, so there will be n in nc n minus 1. So there will be, let me write down over here. So there will be nc n minus 1 subsets. There will be nc n minus 1 subsets in which these bit position will contribute 2 to the power b, where this is the bit position. So if you can do one thing, if you can remove this contribution, you know that this will contribute for sure. If you can remove this contribution from this bit position, this bit position, this bit position, and this bit position, because you know that this contribution is hidden in f of n minus 1. So if you can simply do f of n minus 1 minus whatever the contribution of all of these bits are, right, where you guaranteed know that all these bit positions are determined and they are set, then if you remove these, right, then once you have removed this, then you can notice that there can be no longer any carry forwards that remain. Why is that true? So notice that we are computing f of n minus 1, and we have already removed the contribution of all the bits that were all ones in all the elements, right? So now we know that each bit position can have a maximum of n minus 1 ones only, right? So there can be two cases. Either a particular bit position has exactly n minus 1 ones, or less than n minus 1, but it cannot have greater than n minus 1 ones, because we already removed the contribution from f of n minus 1, right? And also it cannot contribute anything if it is less than n minus 1, because we saw that it will contribute something into 0, right? So this means that whatever remains, like if you have the binary representation of 1 1 0 0 1 1, then whatever remains over here, this is the contribution with the factor of 1. No carry forwards are involved, because if there is a 1 over here after removing the contribution of all the bits that were equal to all ones, then this means that if there is a 1 remaining over here, it means that there is exactly n minus 1 set bits, and they have contributed n minus 1 c n minus 1, right? So that's why this number can now be purely expressed after removing the contribution of f of n. This number can now be purely expressed as something like this: 2 to the power x into 1 plus 2 to the power y into 1 plus 2 to the power z into 1 plus 2 to the power p into 1, etc. And what do these x, y, z, and p, etc. they represent? They represent that in all of this bit position x or the bit position y, etc., the number of set bit count is equal to exactly n minus 1, because we know that it cannot be less than n minus 1, because if it had been less than n minus 1, then it would have contributed 0. But if it had been greater than n, then we already removed their contribution. But if it is equal to n minus 1, then it will contribute exactly one subset, right? And hence we can conclude that all the So after removing the contribution of f of n minus 1, basically removing the contribution of all the set bits from the previous iteration, all the set bits that remain, they indicate that these bit position have the total count equal to uh, n minus 1. So then you can repeat this process for each n, starting from n, then going to n minus 1, then going to n minus 2, and so on, right? So at the end you will have an array that contains for each bit position what is the maximum, what is the total number of set bits that you have that respect that f of I condition, right, for each I. So yes, this was the problem. Now, no need to worry if the explanation of the second part looked a bit convoluted, because even if you did not get that, it's fine. You can try run some test cases and see why removing that contribution gets rid of the carry, right? But I think if you can take away one thing from this video is this, that whenever you are involved with something that has to do with carry, then you can stop worrying about the carry by just focusing on the contribution, right? But in the second part of the video, we also saw that whenever you want to whenever you have the contribution, right, and you want to remove the carry factor, then you can simply remove the contribution, and that will get rid of the carry. So it goes both ways. So this part is actually very easy to figure out, easy to see, like why if you just multiply 2 to the power I by the count, this will get rid of the carry. You don't have to worry about the carry. But if you want to go the other way around, this part is a bit difficult to see, like why subtracting this number and making all the coefficients as 1 gets rid of the carry factor. Okay, so take some time to think about it. And yes, I hope you found this video useful. If you have any feedbacks or suggestions, do let me know in the comment sections. Thank you.